events such as earthquakes, dike intrusions, and volcanic eruptions that likely accommodate that plate motion through episodic events along localized zones of deformation. So I'm going to fly straight into the data because Valentine's really done an excellent overview of the locations and the background tectonics. So kind of the best overview of the plate motions comes from GPS data that's been collected over the last 20 years or so. So for the Danakil region specifically, the best data actually comes from GPS stations along the coast of Eritrea and in Yemen and Saudi Arabia. So these arrows show the motion of GPS stations, with the longest arrows at about 20 millimeters per year, 2 centimeters per year. And it's all relative to a fixed Nubia plate. So you can see some classic characteristics of Red Sea extension. So the Arabian plates extending northeast at around 2 centimeters a year away from Nubia. The rate of this extension doesn't vary significantly over the scales of this map because the polar rotation of the radar of the system is very, very far to the north. However, as Valentine said, it gets very, very complicated when you get into Afar. So these GPS vectors, you can see at the northern end of Afar are basically zero, there's no extension. But you can see the vectors increase in length progressively as it goes southwards along the Danakil block to a full spreading vector in the far south. So basically what's happening is the extension is being transferred from the mid-ocean region in the Red Sea to the south, and then when you get on land, that's taking up the extension, and the extension is dying down in the marine part of the Red Sea. So there are formal plates, there are ways of modeling GPS data, and that's been done in a number of papers, and this is pretty much the state of the art in terms of modeling these plate motions. And at the moment, they've only been modeled in terms of localized plate deformation. So you can see the plate motion, the plate boundaries are just single lines, and then these move to try to replicate the observed plate motion. And that's shown over here. So this is one of the best fit models, and it shows you go full spreading in the marine part of the Red Sea. When you go south, that extension dies out in the marine part, it's transferred on land in the Danakil Depression, you get progressive increase of extension southward. So the net sum of these vectors is the same all the way along the system. You just transfer the extension from the marine part to the on-land part. This model shows one block of the Danakil plate. You can fit the data pretty much equally well, if not slightly better, if you have two plates, like Valentine said. If you divide the plates into two, roughly running through the Nabro line or halfway through the plate, you get pretty similar modeling results. You can fit the data very well. And that explains some of these peculiar, you can see the subtle changes in the GPS vectors. Yeah, that's why you need this additional plate boundary potentially. However, in reality, we know that the plate boundary isn't localized. So we know that through a number of data sets. And this shows earthquake data collected since 1960 on global catalogs. This is the NEIC catalog since 1960, showing earthquakes over magnitude 4 or so, colored by depth. And there's focal mechanisms over the same time period for earthquake magnitudes of 5 and over or so. And you see some characteristic patterns of Afar. So, for example, most of the earthquakes, or a significant number of the earthquakes, are along these magmatic segments in the roof, and they're definitely not forming a straight line like the GPS model. You have magmatic segments 100 kilometers long that step laterally in different places. So the Ertale segment steps east, the Patale segment, and then also you get a stepping of the deformation zone, the Baku segment to the east as you go to the south, and that's where you have the majority of the seismicity. In the Danakil Depression specifically, you see significant along roof changes in the amount of earthquakes. So you can see a cluster of earthquakes in the northern end. There's a lot of earthquakes in the north, and then also the south has a fair number of earthquakes, whereas the middle part of the Danakil Depression, where you have the Ertale range, has fewer earthquakes. This is hinting at a long roof change at the mechanism of extension. So you basically potentially have more extension by faulting in the north and the south through these earthquakes. Another major point is that you've got earthquakes along the western roof margin that form roughly half of the earthquakes in total. So in terms of the seismic deformation, we have roughly half occurring in the rift axis along the magmatic segments and half on the rift margin. So the earthquake data doesn't give you a picture of the total amount of extension, because we know that a lot of extension happens through dike intrusion, which doesn't necessarily cause earthquakes. So the earthquakes are just showing the seismic component of the deformation. But using other techniques like INSAR, we can fill in the gaps in terms of the distribution of the strain to form a better picture than we get with GPS alone. So INSAR is a technique that relies on differencing 2 or more than 2 radar images, looking at the difference in phase or the position of the 2 images in relation to each other. And since we know the wavelength of the radar wave, we can compute the amount of ground deformation. And this is very good at increasing the spatial resolution of our deformation maps. So this has been done in a number of studies in Afar. So this is one from Noor from a couple of years ago, where he combined multiple satellite tracks and combined it with the GPS data in the region to make a sort of better spatial picture of the distribution of extension and also vertical motion. So this map specifically shows the component of extension in a rift orthogonal sense. So red is showing extension or motion in that direction. Blue is small components of compression. So you can see most of the map is red because it's a rift. So some key features of the map, you can see that the colors change from more white to red as you go southwards. So that's just showing this increase of extension rate from north to south, like you have just from the GPS alone. But you can see clearly this change, the step in the locus of extension from the Danakil Depression to the west, the Bahu segment. So you can clearly see this step from one segment to another in terms of the locus of extension. Another key feature of the map is if you draw cross section. So the cross section I'm showing here is through this, that one, through the Earth range, straight through the middle. And that's showing here, you've got the topography at the bottom, and you've got the extension as this red line. So no extension as you get a gradient, that's showing you the locus of extension. So you can see that the extension is localized roughly in a 50-kilometer wide zone about the magmatic segment. So you don't have a very, very localized zone. It is distributed over several tens of kilometers. The vertical motions are shown in blue. And for this particular profile, we've got around about 1 centimeter of subsidy per year. These are annual rates. And then the extension is around about 1 centimeter per year across the Earth segment. So this provides a much better picture of the spatial distribution of strain beyond GPS. One limitation is both the GPS and the INSAR. We still have very limited constraints on the amount of extension on the rift margin. So the reasons are we don't have very many GPS stations across the rift margin in Ethiopia. And INSAR doesn't work very well because of the topography. You don't get coherence between different radar images because of the steep topography. So we still don't have quantitative constraints to the extension in this area. So for example, in this particular model, they basically make synthetic GPS stations all along the margin and just put that as the Nubian plate. So this paper and the other papers don't constrain at all the amount of extension across the margin. So it's a major unknown. So we have a lot of constraints on the nature of these rapid episodic events that cause a lot of deformation very suddenly. And these come from a number of sources. So for example, one of the first examples, good example of major crises in the area was from the 1993 Bada sequence. And this was recorded by seismicity and then field observations of faulting and ground cracking. So in this particular area is about a few tens of kilometers north of Dalal in the rift axis. And then around about 20 or so earthquakes over magnitude 4 reported in the global earthquake catalogs that locates, it's roughly about a 50 kilometers long zone in the rift. And it's co-located with where there's evidence of ground cracking in the sedimentary basin in the axis of the rift. So in the first paper by Ogubowski, he ran a seismic station in Eritrea around about 100 kilometers to the north in Asmara. And he recorded on that specific station, because it's very close, a very good record of the seismicity through time. And that's shown with the histogram. We've got the number of earthquakes about per day over a time period of about a minute. And it shows initially a small number of earthquakes and they're ramping up to a high seismicity rate and progressive decrease through time. But from these data alone, it's quite difficult to determine whether these are faulting only deformation or earthquakes induced by dike intrusion. So in collaboration with Ogubowski and also Joe Rouge, we really looked at the data. Ogubowski had kept the arrival times of the P and S waves at that single station, which is perfectly parallel to the orientation of the rift. So we could effectively produce a single station earthquake location, its position along the rift axis through time. And that's plotted on this diagram. So this is a long rift position against time in days, around about a month. and the colors are earthquake magnitude. And so you can see some characteristic patterns of dike-induced seismicity. So you can see the earthquake start and then migrate, in this case, two directions progressively through time. So it looks like you've got a magma source and dike intrusion in two directions. The biggest earthquakes don't happen at the start of the sequence. They're distributed through the sequence. So it's not a main shock aftershock sequence. It's more like fluid-induced earthquakes. And also the biggest earthquakes are at the tip of this deformation zone, which is very common of dike intrusions. The biggest stress change that the dike tips, which causes the biggest earthquake. So the interpretation is this is a dike-induced earthquake. There was a magma intrusion subsurface that induced the seismic swarm. So these days, since 1993, actually, it's quite strange. The Butter sequence basically was just before the first radar acquisition. So we just missed being able to use INSAR to study that sequence. But for all the sequences since, we can better understand whether seismic sequences are related to only faulting or dike intrusion by using INSAR as well, because the ground deformation pattern that these different sources produce is very characteristic. So with INSAR maps, basically the deformation pattern is shown by a contour map with ground motion, each contour 2.5 centimeters of motion. And magmatic sources such as sills and magma chambers or mogi sources, they form circular shaped deformation patterns. Dike intrusions tend to form these characteristic butterfly patterns of deformation, whereas a fault only tends to produce only half of the butterfly. So it's very easy to distinguish these sources. So one of the first good examples that happened that's really highly relevant for our study area is evidence of dike intrusion beneath our study area. Basically, in 2002, there was an earthquake 5.5 reported by the global catalog. And then retrospectively, probably about 7-8 years after, the interferograms were processed. And I showed a number of key features. So the earthquake location was there according to the global network. But then the interferograms showed very spectacular deformation. There's a pattern of subsidence at Dalal volcano, and then there's characteristic butterfly pattern of deformation from dike intrusion. That's very complex in some parts. It's more complicated than just a pure dike deformation. So the good thing with these deformation maps, they can be formally modeled with a subsurface model. And in this case, the deformation can be well modeled with a magma chamber to simulate the subsidence of Dalal at about 2 kilometers depth. Dike intrusion, about 10 kilometers long at about 5 or 6 kilometers depth, so like this. And then you need a normal fault on the western side to simulate this more complex part of the deformation pattern. So it's a dike and faulting combined deformation. So then by looking at some seismic records, so Atelier runs a station here in Addis Ababa, which was the closest seismic station to this specific event at the time. But it's still high quality data, and you can see evidence for microseismic events before this earthquake slips. So it's really good evidence that basically the sequence of events was the magma migrates out of that chamber into the dike and induce the fault slip. There's been lots of deformation of Dalal since. So for example, between 2008 and 2010, there was a pattern of strong subsidence at Dalal of around about 10 centimeters per year. That can be modeled with a similar position magma chamber from magma withdrawal. And then recently, there's been even more deformation at Dalal. And you can see the poster by Carolina Pagli with her work and work done by our PhD student, Burhan Kabede, that has an up-to-date picture of the deformation pattern of Dalal. There's been a number of deformation events associated with volcanic eruptions as well. So this is a good example from the November 2008 eruption of Alafila, which was was one of the largest basaltic eruptions in Africa in the last 100 years. There was a basaltic lava. Well, we don't really know the rock type. It's basic. To the east of the Ethiopia range, between Ali and Alafila. So during this eruption, there was strong deformation. There's sort of lobes of deformation that show 2 meters of subsidence. And in the middle of that, there's a more complex pattern of deformation. So when you need to model this, you have to have a very, very shallow sill that deflates about 1 kilometer's depth. And then you also need a dike intrusion above it in the middle of the sill. And then you've got your volcanic eruption at the top. So basically, the interpretation is that the magma was removed from the sill, and some of it intruded the dike and some erupted. When you balance the volumes, the volume of the dike intrusion and the eruption equal the sill. So basically, half of the magma that left the sill intruded and half erupted. There's also a sort of subtle broad pattern of deformation around the event that you need a deeper magma chamber that deflates to replicate the deformation. So you get similar kind of stories for the other major eruptions in the Ertale range. So in 2017 to 2019, there was a long-going volcanic eruption from Ertale, and at the beginning of which there's deformation that you need, again, a shallow sill and a dike intrusion to simulate. And then also for the Navro eruption, there's a similar picture. You have a complex magmatic system associated with this major eruption. So the picture is basically the magmatic system along the Ertale range is complex, but shallow. You have a shallow magmatic system, which is quite unusual. And it's only really seen at fast spreading mid-ocean ridges. So the interpretation of that is that you need a high magma flux to sustain these very, very shallow magmatic systems. So there have been examples of fault-only deformation as well, but these, again, similar to the pattern seismicity, have only been at the lateral tips of the Danakil Depression. So at the southern tip, there's been a number of oblique slip earthquakes reported by the NEIC catalogue in 2007, 2018, one is shown here. And they do produce ground motion that can be modeled purely with an oblique slip fault. So the deformation from the surface is perfectly consistent with the earthquake. So it's no magma involved, just pure oblique slip faulting. And the interpretation of this is basically you've got a component of oblique slip between the Ertale segment and the Patale segment, because the two rift segments need to link through a complex fault system. And you can see more information about this and how this relates to the geology of the area in the poster outside. At the northern end of the Danakil Depression, there's also good evidence of fault-only deformation from INSAR, but in this case, it tends to be only normal faulting, not oblique slip faulting. This is work recently published by Alessandro. So there's a magnitude 5 earthquake and subsequent magnitude 4 earthquake in the Bada area again in December 2022, so just half a year ago. And through these days, the radar images are collected so frequently that you can sometimes decompose the pattern of deformation through a long earthquake swarm. The radar images are collected every 7 days or so. In this case, we were able to decompose the ground deformation from the main shock, from the magnitude 4 aftershocks. So the main shock is shown here. So it's about 10 centimeters of subsidence, and it's not a butterfly, it's half a butterfly. So you need it to simulate this, you need a normal fault that's dipping to the west. And then for the aftershocks, you then need another fault about here that's dipping to the east. So in total, you've got deformation forming sort of a mini graben. And this is offset slightly to the west of the rift axis. It's not in the axial zone, about 5 kilometers to the west. So there's also been a recent magnitude 5+ earthquake just last month. That's on the western side of the Gulf of Sula. That does produce measurable ground motion as well, but it's very, very subtle. The ground motion is very subtle, which, considering the magnitude of the earthquake, basically implies that the earthquake is very deep, because basically the deeper the earthquake goes, the more you can hide the deformation of the ground motion. You don't cause ground motion from a very, very deep event. So the implication is that it's a sort of unusually deep earthquake, and this hasn't been modeled yet, but it's probably going to be, provide insights. So the overall picture this is painted is that you've got, again, similar to just the pattern of seismicity, you've got fault-only related deformation at the tips of the Danakil Depression, but then a strong magmatic component in the Ertale range. So we do have constraints on the fine-scale fault structure for microseismic projects. So there have been 2 microseismicity projects in the area in the last 10 years. So the first one was around about 10 years ago. For 2 years, we had 10 seismic stations for Danakil Depression, about 20 kilometers spacing, supplemented by a number of stations in Eritrea. And you're able to locate the earthquakes to sort of kilometer scale accuracy, in contrast to the global earthquakes, which have tens of kilometers location error bars. So you get a much finer picture of the locus of deformation. You see it's the rift axis and the rift margin. When you plot cross sections of the earthquakes, it's across the rift with the crustal thickness shown here. You can see that most of the earthquakes are basically in the mid crust to upper crust, with some lower crustal earthquakes. When you look at the western rift margin, basically in this particular study, the sort of crude pattern or geometry of the seismicity kind of hints at the main faults being antithetic and being associated with the marginal graben system. So these are some of the seismic stations that we use. It's quite challenging to deploy in the area of the heat. So this is the station of Kusawad to the west of Otale, and this is the station of Afar military camp. But we did actually have very, very good data recovery and no vandalism. So Frank White has reinterpreted this data and relocated it and aligned it to the structural geology and provided really good evidence that the main fault system is antithetic and associated with these problems. So I'll conclude there. So basically, overall, the deformation of the Danakil area is driven by this rotation of the Danakil block. And we are generating much better understanding of the distribution of strain by incorporating things like inside seismicity with a complex fault system on the western rift margin. But it's still unknown how much extension in total, because we only have seismicity, we don't have GPS INSAR to measure the total extension there. And in the Danakil rift, there's strong indications of significant long rift variations in the amount of magnetism and faulting